Good afternoon, everyone. We're going to go ahead and start off our second semester with Chapter 18, talking about electrochemistry, and again, transitioning from the concept of chemistry, from the theory behind a lot of these things, and actually starting to move into the application phase, where we're going to study the reactions a lot more. We're going to look at reaction rates and the different things of how we can manipulate those same reactions to behave a certain way based on our preference. Now, with electrochemistry, we're going to go ahead and get into some things that we already know. And I believe this is actually the perfect time because we're right on the heels of redox reactions. You all have gotten a lot of exposure to, oxidation, reduction overall, figuring out reducing agent, oxidizing agent. So you're going to see more of the same in this unit. The part that's going to be new is as we transfer into this section, how do we change from chemical energy to electrical energy? Again, we have this energy stored in these bonds and all these types of things, but how can we use that to benefit us? So, the first and most common for many of you will be your cell phone. Most of you can't live a day without your cell phone, can't go 5 minutes without your cell phone. But each time you charge it, what are you actually doing? How is that going to affect your battery life and all those types of things? And how do you actually create energy coming from the wall if we know that it's just the flow of electrons? Now, the first thing that we're going to look at or review is going to be looking at how to balance half reactions. Well, if we look at this overall, we know the process. We split our reduction and our oxidation half. In this case, we have our manganese that's being reduced from a +7 oxidation state down to a +2, whereas our iron here is actually going to be oxidized, losing a single electron. Why is it multiplied by 5? Well, remember that whole difference in number of electrons. This one was getting rid of 1, whereas this one was somehow gaining 5, so we had to make sure that they add up. You can tell just by looking at this, it's in an acidic solution. How do you know? Well, we have this H+ ion that's sitting right here. So if we have hydrogen ions present with our water on the other side, we know that this particular reaction happens in an acidic solution. Now, this is one that I actually would like you to go ahead and take your time and do. Go ahead and pause it here because I believe that everyone should be able to do it without too much of a problem. I'll wait. Now that you come back after doing it, you should be able to go ahead and pull off your reaction. One, knowing that, again, we're still dealing with manganese being reduced and bromine being oxidized. It says in an acidic solution. One of the things you'll note, and this is just something to note for all future times, usually if you see this process happening from manganese or permanganate ion down to manganese 2 ion, it's usually going to happen in an acidic solution. You may want to keep that just in the back of your mind because it tends to come up every once in a while. Now, after balancing everything out, you had your reduction in your oxidation half. This is what you're going to end up for your final reaction. So you should be able to check what you have versus what's on screen now. If something doesn't line up and you're unsure of what's going on or why it doesn't line up, feel free to jot down any questions that you may have so that we can get them answered in class. One of the things we want to make sure that we're doing is, I don't want you just watching the videos just to say, yeah, I stared at a screen. But I want to make sure that you're getting the most out of it. So if questions are coming up, things that are unclear, don't be afraid. Please, please, please ask those questions, and I'll try to get them answered in class as best as possible. Now, when we have this process, this redox reaction, one of the things we found that would actually help us in the long run is if we didn't have this reaction happen in the same container. Well, why? Well, the reaction only needs a certain amount of energy to occur. So anything extra, like if you felt the beaker and it warmed up, that means that's extra energy that's being given off. We want to somehow harness and control that energy to use it for something. Enter galvanic cells. Now, this is just going to be the basic device where we have energy change from chemical to electrical. One thing I want to point out here, notice that it says it uses a spontaneous redox reaction. Spontaneous, of course, we know means happens on its own without any extra input. Now, the reason why I want to point this out is when we deal with galvanic cells or voltaic cells, as you'll see, they're always going to be spontaneous. So whichever way the electrons move, they're doing that on their own. But when we get further down the line, we're going to talk about electrolysis. Now, for electrolysis, we have to put in energy in order to get the reaction to occur. So galvanic, spontaneous. Electrolysis is going to be we input energy. Now, because we've separated this reaction into two separate containers, but we still are transferring electrons or electricity, if we have the system set up as it is here on screen, we're going to run into a slight problem. Well, what do you mean? Well, we know that manganese is what's going to be reduced, which means if it's being reduced, that means that the electrons are flowing this way. Now, if the electrons are flowing that way, that means eventually what we're going to do is we're going to end up with a slightly negative here and a slightly positive here. Why? Because we're going to have, as the electrons go that way, we're going to end up with more of these iron 2+ ions just hanging out in the water or in the solution. Now, if we have a buildup, a positive on one side, negative on the other, and there's no way to sort of balance it out, our reaction, our circuit stops. So we have to figure out a way to complete the circuit. One way that we do that is we use what's called a porous disk. Now, it really is just a disk where we actually have very, very small channels, extremely small, so that ions can flow back and forth. Now, note that in here, we don't have a changing or an exchanging of the ions in solution, but many times it'll be another substance that wouldn't hinder the reaction, something that will be effectively neutral. Now, the place where the electrons are coming from is what we're going to call the anode, and the place where we saw the electrons going to is going to be the cathode. Okay? Now, oxidation is what's going to occur at the anode, and reduction is what's going to happen at the cathode. A couple ways to remember this, and I'll go ahead and write this on screen so it's a little bit easier for you guys to see. The way to remember, we're going to look at red cat. Reduction happens at the cathode. Because reduction happens at the cathode, we're going to see the cathode grow in size. Okay? Whereas when we look at the anode, this is where, of course, our oxidation is going to happen, which means that we're also going to see this shrink in size. It will look like over time, like it deteriorates away. Now, the other thing that we can use the porous disk as we specified before, but the other thing we can use is what's called a salt bridge. Now, the salt bridge is usually going to contain a gel of a strong electrolyte. This is again going to allow for us to have transfer of ions without them affecting the overall reaction that's happening. So it just prevents us from having a buildup of positive and negative. Okay? Now, when we have this system going on, it's great that we have this sort of cell happening. We want to make sure that there's some way we can actually measure what's going to happen or how much energy is being transferred in this process. So in one container we have the oxidizing agent, and that is actually pulling electrons through the wire from the reducing agent that's in the other. That pull that's happening, that's what we call the cell potential, or E cell, and that's what you're seeing right here. Okay, that strange symbol, but we normally actually put it this way, where we just say it's E for the cell. Okay, now this is going to be measured in volts, which you can see there at the bottom, 1 joule of work per coulomb of charge transferred. This is looking at how many electrons are being exchanged based on the energy that's being produced. Now, if we're looking at a galvanic cell in what we call its standard state, we're looking at this cell in what we say here. We have 1 molar solutions here, 1 atmosphere of pressure and 25 degrees Celsius. This helps us to sort of work through and determine what the cell potential is going to be for the overall reaction. Okay, now for most of what we're going to start with, we're going to be here, standard states, so it just helps us to figure out which way the electrons are moving and when. Now, if we're looking at a half reaction, or at a reaction overall, and we're looking at the half that gets reversed, because of course, usually the information is given to us, at least in the table, as reduction. But we know that in a redox reaction, something has to be oxidized. If that's going to happen, we have to look at the fact that the sign is also going to be reversed. So if something has a positive value when it's being reduced, but we find that, hey, in this case it's being oxidized, we're going to flip the reaction, which is also going to flip the sign and make it negative. When we want to make sure that overall that our cell potential for the entire reaction is going to be positive, and that's what we're seeing here. Okay, that's what's going to help you to determine what's the anode, what's the cathode. Now, pay attention at the top here, and I want to highlight this. You also have one that I gave you in your reference pack, but table 18.1 is where you're going to find a table of these reduction potentials. Okay, the more positive the reduction potential, the more likely it is to be our cathode. Now, let's look at this example. We have overall this reaction is given to us, and we can all see the process that's happening. If we use our half reactions, our reduction potentials, these are the values that are provided for us. Okay, for the reduction of iron 3 to iron 2, we give off 0.77 volts, and from copper 2 to copper metal, 0.34 volts. Overall, we're going to look at and balance this out, but we notice that instead, according to our reaction at the top, it doesn't show copper 2 going to copper solid. It actually shows copper solid being changed in copper 2 ions. That being the case, that means we have to reverse the sign, reverse the reaction, reverse the sign. Now, of course, balancing out what we have here for our iron, notice that our standard cell potential for our iron doesn't change. Even though we multiplied the number of electrons, it doesn't change that value. It doesn't change our standard potential. Now, once we have everything balanced, now it's just a matter of plugging it into our formula. Now, the formula is given to you right here. E standard cell, that's what that symbol there means. E standard cell equals E standard for the cathode minus E standard of the anode. So I can literally just plug in the values as they are from the table, and I'm going to end up with 0.43 volts. This helps me to determine, okay, if I have this reaction happening in my galvanic cell, this is how much energy, this is how many, as we looked at, the volts are joules per cathode transfer, Coulomb transferred. We're going to have 0.43 volts transferred across that wire. Now, last thing to do for this part, and then we're going to go ahead and take a break for this next one. When we have our galvanic cell, we're going to have to show it in some way, shape, or form. And so, what we do is, instead of writing out, we have this whole process going, we use what's called line notation. Now, the anode's components are always on the left. And so if you look at the bottom, I'm walking you through as we see the example here. We have magnesium being dropped into magnesium ion. So that component is always on the left. So we go magnesium solid is our main electrode, one line. Then our solution is magnesium 2+. You would also include, if you have the information, you should also include the concentration. So if this was a 1 molar solution, then you want to make sure that you include Mg2+, 1 molar. Then we're going to do a double line, which is going to represent our salt bridge or porous disk. Then on the other side, the cathode. In this case, it's aluminum. So again, aluminum ions. And if we know the concentration of the solution, 1 molar, 0.1 molar, whatever the case, we're going to go ahead and include that in that space, then a single line, and then aluminum solid being our other electrode. Okay? Now, again, we're going to have to practice this. Don't worry, it's okay. We'll make it through. But if you are lost, make sure you write down questions. I don't want anybody to be lost as we continue to go through this. So just take your time. We'll walk through it in class a little bit. And yeah, that's where we'll end it for now. I will see you all in class. Have a good one.